Welcome. So we will look at another building block of vector calculus, which is curl. So what we did before, we did gradient. So remember, like we did gradient that looks something like this, gradient of a function. So basically gradient, that's a vector, that's a scalar, and it gives you like a vector. Yeah, we did this before. We did divergence. So divergence. So like we have this guy, divergence of like a function. So that is a vector, and my function is a vector, and then the output would be like a scalar. Yeah. Uh, so that will tell me something about like steepest ascent or descent. That will tell me something about expansion or contraction, sources or sinks. And last of these guys is the curl. So here, curl, this is like the gradient. That's like a vector. And this is not dot product, but like cross product of like another vector function. And that will give you like a vector. And that tells you something about rotation. So rotation, sources and things like expansion, contraction, something like this. And then here gradient, like steepest ascent or descent. And these form the basic building blocks also of all our conservation equation and any modeling that we will be, or like numerical, like physics-based modeling that we will be doing, whether like these are analytical or numerical solutions. So let's just get started here. So blah blah blah. Given a vector field, so this guy is a vector, so we know how to represent a vector field. So I have to put this arrow here. This is like fx of y, z. So that would be like f1. Sorry, not fi. F1, yeah, in the I direction plus F2 in the J direction, yeah, plus F3 in the K direction, yeah. Uh, so this is like my first function. And remember, like car, let me put it here, car, that is what? Like that is like your gradient, like your, this is a vector, cross product by your function, which is like a vector, yeah? So that is basically what we are interested in, yeah? And this will, like this cross product will give us like a vector here. So we expect like to get a vector, not to get a scalar. So remember like this guy, like the gradient. Gradient does not require like this arrow here because by definition it's a vector, but I just put it to re-emphasize the concept so that you know that I'm expecting a vector, but it does not need this. So remember this guy, that would be like parture xi, yeah, here. Sorry, just put him here. Parture. Oh, sorry, the gradient here. Let's be equal parture x parture I plus parture y parture j plus parture z parture k. Yeah. So what do I want to do? What I want to do, I want to like get this guy here. Yeah. And I like do cross product with this guy here. So remember, I can also express this in different notation. Remember, like I can express a vector in this notation, or I could also express it in this notation, parture, parture x, parture, parture y, parture, parture z. This is also like a vector. Cross product by f1, f2, f3. So this is a vector and this is a vector. And how to do this cross product, if you remember from linear algebra, like if you took linear algebra, we'll have a module about linear algebra, but I will just show you like how to do this. So basically, like to solve like this, to make this cross product, like what you do, so here this is like your this parture f. Okay, what you can do, you just make like this is called like a determinant, and this determinant you put like your I, J, K, yeah, and then here you put like your first function, so that would be parture, parture x, parture, parture y, and parture parture z. And then here you put your second function, f1, f2, and f3. Yeah. And then like how to solve this determinant, So basically like to solve this determinant, we expecting to get a vector. So we expect to get something in ijk. So we first solve for I. So we first solve for I. Yeah. So how to solve for I, that's like how you do it. Like you cross this guy, and then you multiply this guy with this guy, and you subtract it from the multiplication of this guy with this guy. So what is this? So that would be parture f3 here, parture y minus parture f2 parture z. Yeah. And that would be like in the I direction. That's the curving like in the I direction. Okay, so that's I solve it for I. Yeah. Plus, I need to do the same thing but for j. So how to do it? You cross this guy, and again you multiply this guy with this guy, and you subtract it from this guy with this guy. So this is here parture f3 parture x minus parture f1 parture z. Yeah, and then you subtract. Okay, that's in the z direction. Again, what do you need to do? You need to also solve for k. So plus k. So how you do this? You cross this guy with this guy, then you multiply this guy with this guy and subtract it from this guy with this guy. So let's do it. So that is parture f2 parture x minus parture f1 parture y. Here's a plus. And that is in the k direction. So basically you get something that looks like this. Yeah. Here's the equation. Like so I got like the same equation here. Yeah. 3f2. Yeah. So let's do an example. Like yeah. It's so here like finds a car like so this is a FE example. That should be easy pointed FE example. Finds a car of a vector field like this guy. Yeah. So here I just want to find the curl of this vector field. So parture here, this is a function, like this is a vector, this is a vector, and you see this is all a vector. So what is this? So F3, what is F3 here? Like this is K here, so this is F3 0, yeah? That's like F3. So parture F3, parture Y, that's like 0, yeah? Parture F2, parture Z, where is F2? Do I have any Z here? This is all constant, so that will be again minus 0 in the I direction, yeah? Plus parture f3 parture x, that's like another 0. Parture f1 with respect to z, do I have any z here? No, this is a constant, so this will be another 0. So that's like in the j direction. Don't forget to put this hat, yeah? Doesn't matter. But anyway, and then parture f2 parture x, where is f2? So parture f2, so e to the power x, like do you remember like the derivative of e to the power x with respect to x, that is equal to e to the power x, yeah? So this guy is a constant, this guy is a constant, so parture f2 with respect to x, I get the same guy, y, yeah? Minus f1 with respect to y, so and like this guy with respect to y, this is like a constant, this would be 1, so I will get 7 e to the power x in the k direction, yeah? Sorry. I do something? Sorry, I did a mistake. I'm not looking here. I'm looking. See, I mean, you can that. So that's the type of mistakes that you can do in your homework or in your exam. You will like overlook something. So here, parture f1 with respect to y. This is f2. So this is like my f2. This is my f. So this is like my f1. This is my f2, and this is my f3. So here it's telling you parture f1 was like with respect to y. I don't have any y here, so this would be like minus 0, and that would be in the k direction. So the diversion of this function is equal to 7exy in the k direction. That's basically the divergence of this line. So what I'm trying to do here, I just did like this example for you, so you can visualize these concepts, or like maybe when you visualize these concepts, you can have a better understanding for them. So we can model a hurricane with radial varying curve, where the wind field of a hurricane decreases in strength as we move far away from the center. So here we have like the hurricane center, highest strength will be here, and as we move away from the center, the strength will decrease. The velocity component in the xy plane is given by this. So basically, this is the velocity component in the I direction and in the y direction. And basically, it tells you, so here, that basically tell you how far you go away from the center, yeah? So let me just walk you through this equation. This is an equation you can use actually. This is an actual equation. So A is a constant representing rotational strength of the hurricane near the center. So basically this tells you the strength of the hurricane, like let's say 3 radian per second or whatever. Yeah? That basically radian per second. That tells you about the strength, like the strength of the hurricane, yeah. And y, this is like our coordinate in the plane, and xy, this represents the distance from the center of the storm, like radial distance. So this is here, and represent like how far away I am from this storm. Yeah, that's basically represented by these guys. I'm asking you for a few things. Find the curl of the vector field. So I want you to find like the curl of this vector field. So you know how to do this. So basically the curl of this vector field, that is equal like this guy cross product with this guy, and that will give you the curl of like f. That's how that will give you the curl of this. Interpret the physical meaning of the far as a function of distance from the storm. So basically you will see how this curl increase, like is very high at near the center, and like decreases as you go away from the center. And visualize the wind field and curl variation. Like you visualize the wind field and curl variation. I solved this for you with Python. The codes are all like, for each module I post all the codes, like whether Excel or Python, that I use to generate these things, so you can look at them. But here is the solution, and the important part is like the interpretation, because like once if you interpret this, then you will get a better understanding of what is going on, rather than just seeing this abstract mathematics. Okay, so this is my function. Yeah, this is like my f1 and my f2. So here's my f1, this is like my f2, this is the curl of this guy. So that would be basically, it's only like 2D, not like 3D as the other ones. So you get something like this. And then if you get the partial derivative of f2 with respect to x, you get something like this, looks like this. Partial derivative of f1 with respect to y, you get something that looks like this. You put them here, then you get something that looks like this. Yeah, so, and you see here, it's like the distance squared, and that's very important. Like I will talk about this later. But so this is the curl of this function. Now let us visualize this curl. Let's just plot it. Like it's plot its like magnitude and direction. And just as you expect, like the curl magnitude or verticity, like verticity, it's very like a big magnitude towards the center, and it fades away and becomes smaller and smaller as you wave away from the center of the storm. And this depends on like these distance. Yeah, so basically like, so near the center, like this distance, uh, like as this distance is approached to zero, the car becomes the largest. So here, like you have the largest car, like the largest verticity, the largest rotation. This is like a tornado type of thing. So that would be like the center of the tornado. That will you have like the become largest, indicating like very strong rotation. Yeah, at the storm core. Yeah, versus on the other hand, as x plus y like goes like to infinity, Like, see, so here this is like as this goes to zero, this become very large, but as this goes to infinity, like as the denominator goes like to infinity, this just becomes this fade, like this car approaches to zero. So you see this car here and this rotation here is like fading, it's approaching to zero. You don't get this much rotation, you don't get that much wind, which is what we expect, and like the hurricane basically you will dissipate and just you will not feel it. Yeah. So basically, what the important thing we see here is that this car, like according to this equation, it just changed with distance. As we go far away, this become like not as aggressive as we are like near the center. But another interesting thing which you see in this equation is that this is non-linear. It's not so like let's say I am here, like the strength of the hurricane, let's say is 10. Okay, if I'm 10 meters away, is the strength of the hurricane will not be 1. It's like divided 10 by 1. No, it's like a square. So it faded like with to the power of 2. That's like how it faded. So it feel like, so here it would be very strong here. You get like this, like a strong non-linear relationship. Here will be like still very strong, but like as you move here, it gets weaker and weaker. See how it dissipates quickly and gets weaker and weaker quickly because you have this like non-linear relationship. So the current change with distance reflecting how like the hurricane will typically behave. Stronger at stronger vortices, like you got this stronger vortices, this stronger turbulence or like rotation near the eye, and weaker winds outward. Yeah. By the way, if you want to solve this problem, like the rotations that I used for this guy was like 15 radian per second, like this constant here. And the codes will be online also. You can look at them. Okay. This is a practice problem. I will like solve it in the practice, the tutorial session if you want to look at it. Try to solve it in your own. Don't look at the right answer. I think the right answer is I think it's C. Yeah. So the right answer for this guy is like C here. But try to solve it in your own and then check like the right answer. This is a homework problem. Let's look at the homework problem together, how we are doing in time. Not bad. Okay, so in vector calculus, the diversion of vector field is, so now here I'm telling you the divergence like this guy. Yeah, so this is like this guy. This is a vector function time a vector function that will give me a scalar. So this is a scalar, yeah, that represents the rate of which quantity expand or contract. Expand like source or sink at a point in the field. Exactly, that's correct. Yeah, a vector that points to the direction of the maximum increase in the field. No, that is not this one. This is a gradient. Yeah, that's the gradient of the function. A scalar that measures the net flow of a vector field out or into a point. Yes, remember like I showed you this, let's see here, I showed you this here. Boom, boom, boom. So remember in the divergence, here, remember we've seen something that looks like this. So here, this is basically like the entering flux and leaving flux. They are not equal. So what is entering the system is less than what's leaving the system. So you have like a diversion here is not equal to 0 versus like in a steady state, the input like flux is equal to the output flux in the x direction in the one direction. Then you don't have any you have 0 diversion. You might have rotation here because like you see these things like might cause rotation. So you might have rotation but like 0 diversion, for example. But anyway, so let's get back here. So is this a correct answer? Scalar that measures the net flow. Yes, flow flux in and flux out, because that will also be like a kind of like increase or decrease. So that's correct. A vector that describes a rotation tendency as a vector at a point. No, that is the car. That's a car. Okay, so this is the gradient, this is the car, and this guy is here. So the correct answer would be like this one. Okay. So I think that's all for this lesson, and see you in